Hi, my name is Stephen Jacobs. I'm a senior mechanical and aerospace engineering student in the Statler College of Engineering, and I would like to share with you some of the work me and my teammates Michael Butts and David Rubel have been doing this summer as a part of the Robotics REU here at WVU. Interest in swarm robotics has rapidly grown in recent years. Decentralized control schemes and distributed decision-making are often used in the construction of robotic swarm systems. Because of this, swarm systems can often provide increased robustness and capabilities as compared to centrally controlled systems. These benefits, however, come with an added difficulty in developing general robotic control schemes that can generate emergent behavior and complete a given task. To invoke this emergent behavior, we propose a general optimizable framework for generating emergent behavior in swarm systems. The proposed framework consists of two general components, the structure and the optimization methods. A way to map environmental inputs to robot controls is required to create a useful framework. To do this, we define a parameterized function of local measured quantities that is used to control each agent's velocity. The function inputs are the parameter set, the set of measured scalars, and a set of measured vectors. The parameters are constant values that can be tuned by hand or by using an optimization approach. The set of scalars are magnitude values that any robot can extract from their local measurement information. For example, in many situations, the distance to a goal location or the distance to the nearest neighbor robot would be useful scalar variables to include in the function. The vectors are also collected from the robot's measurement data, but instead of encoding magnitude information, the vectors include directional information, such as the direction towards the goal location or the direction towards the nearest neighbor. These three components are combined using the matrix equations shown in Figure 1 to generate the control velocity for each agent at each point in time. Figure 2 shows a situation where the blue robot measures vectors towards its goal and towards the green robot. Then, using its constant parameters and some measured scalars, the blue robot adds the two weighted vectors together to produce its output velocity. In this method, the sets of scalars and vectors differ from one situation to another and are chosen by a human to best represent what is important to the robots in their situation. Because this proposed structure is parameterized with a relatively low number of parameters, it's possible to use Bayesian optimization, a form of black box optimization, to minimize a given cost function. Black box optimization methods are capable of finding the maximum or minimum of a given function without having prior knowledge of the function. Essentially, Bayesian optimization works by randomly choosing a set of parameters, evaluating the function, and receiving an output value. Using a clever acquisition function, the algorithm continues choosing parameter sets and evaluating the function. Eventually, it is able to reach the global minimum with only a small number of function evaluations. To evaluate this control framework, three main tests were performed. First, in case 1, a simulation was created and a control structure was hand-tuned to produce cohesion and segregation behavior for a large number of robots in discrete groups. For this task, 6 scalars and 6 vectors were chosen, and 36 corresponding parameters were tuned to produce an efficient cohesion and segregation behavior with the limitations of local sensing and agent collisions. In case 2, a simpler task of avoiding collisions with other robots and reaching a goal position was approached. In this simulation, both hand-tuned and optimized parameters were found. For this situation, the cost function penalized the robots for getting close to one another, but also encouraged them to reach their goal locations quickly. The Bayesian optimization method was able to find a parameter set that better minimized the cost function than the human-generated parameters. 10,000 Monte Carlo simulations were run with random sets of parameters to determine if the optimization technique was truly finding the global minima of the cost function. From the Monte Carlo simulation, the lowest cost values were found to be outliers around 255, slightly higher than the cost attained using the optimization method. This framework was also applied on real robots as seen in Figure 7. For this test, 2 robots followed a simple control function with hand-tuned parameters designed to allow them to reach their goals and avoid one another smoothly. The robots were able to repeatedly reach their goal destinations without collisions from a variety of starting positions. As shown in the 3 test cases, the proposed framework is able to create emergent behavior in large groups of robots, is able to minimize a given cost function designed to promote a swarm task, and is applicable outside of simulation on simple holonomic robots. Given these positive results, several areas are being considered for future work, such as applying this framework to other swarm tasks, using it to control larger numbers of physical robots, and possibly combining it with a machine learning approach to mimic biological swarms. Thank you all for listening to this presentation. I hope you have a nice day.